So today we're going to look at section 11-1, exponential functions. We're going to talk about what they are. I'm going to start with a tale, a story. I'm pretty sure it's fake. It's not fake, at least nobody knows it for sure. The story goes that a king asked one of his, game makers. He wanted to invent an interesting game. And supposedly, the game he invented was chess. I think this would have been in India. I'm pretty sure chess comes from India. Anyway, the king really liked the game. He was really happy about it. And he wanted to reward the guy. And he said, I'm the king, whatever you want. And I think you all know that chess is played on a board that's 8 by 8. Here we go. Got almost the full board on there. And this subject, he came up with this deal. He said, okay, Mr. King, on the first square of my board, give me a grain of rice. And on the second, give me 2 grains of rice. And then on the third, give me 4, 8, 16, 32, 64, 128, and keep going until you're all done. The king thought, just a bunch of rice, that sounds fine. How much rice could he want? Well, how much rice is that? Well, the way we would write that is we would say, this is a summation symbol. It means take whatever I've got after here and sum it up. Start with n equal to 0 and go to 63, right? We're not starting with 1, so we go to 64. And on each square we put 2 to the n, right? So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, just like there. And add these all up. And it turns out that if you do that, you get 2 to the 64 minus 1 grains of rice. Well, how big is this number? It's a big number. But I mean, you figure you get a couple bags of rice, right? This is how big this number is, approximately. That's 3 zeros. 3 more zeros. 3 more zeros. 3 more zeros. More zeros. Let's see. So that's 1,000, a million, a billion. You buy a hard drive, a computer hard drive. Computer hard drives have bytes, which are 8 bits. We're not going to worry about bits. So a billion bytes is a gigabyte, right? That's a billion or a trillion. That's how much money the U.S. government's talking about spending in the next bill. That's a quadrillion. That's 1, 2, 3, 4, 5, 10 to the 15th quadrillion. That's 1,000 terabytes. This is a quintillion. So it's like 1,000,000 terabytes, and multiply that by 18. So the total worth of the world at that time is about $300 trillion. So actually what the subject was asking for was more wealth than there was in the whole world. And so the story goes that the ruler solved this problem expeditiously. He just had him executed. That's a fake story, but it's fun. The point is, when you have something like this, a number, we'll just start with like n(x), make that a function. This is what we call an exponential function, because the variable is in the exponent. These things behave kind of a extreme manner, we'll say. Okay. I'm going to get a little more serious now. So let's look at that function for a second. So f of x equals 10 to the x. Let's try and graph that. So might help to have a little table here. X, 10 to the x. So we know it's 0. What's 10 to the 0? Everyone should know this by now. Like the back of your hand. Yes, AJ?
1.
It's 1. So at 0, we have the point 1. 3, 4, 6, 7, 8, 9, 10. 10. At 1, well, everybody knows 10 to the 1 is 10. And at 2, it's 100. It's already off the board. Oop. It's going to go through 1. All right, now let's look at what it does over here. Say minus 1. Well, 10 to the minus 1, everyone should know is 10. So 10. Minus 2, it's 100. I can't even now it just kind of looks like the axis. It never hits the axis, right? There's only a little space between it. So exponential functions, if they're growing, they grow really quickly, generally. If they're we could have a slightly different function that would look almost the same, 10 to the minus x. I didn't draw that very well. It's just kind of the mirror of this. Kind of goes root. This is how quickly, it's going down to 0. Now, this is just kind of vicarious interest here. If you think about exponential functions, like some function, some number a to the x, and you compare that with a polynomial function. Polynomial function looks like what? A sub n to the x sub n plus n minus 1 to the x n minus 1. Well, really, the first you know, the first term is the dominant one, right? As far as how big this is going, how fast it's going to grow. So we can just not pay attention to the rest of it. If we were to take a really, really small number here, like 1 point, it has to be greater than 1, right? To the x, and we compared it with some really big number, I don't know. Say we were using quadrillion, huh? I forget how many zeros. We'll just put 18 zeros. And then we raise x to some really big number. About 10 to the 18, okay? So we're going to take whatever number we put in, we're going to multiply it by a huge number, and then, I have this backwards, sorry. 10 to the 18 to the x. No, this is polynomial. I'm sorry. I'm mixing myself up here. X to the 10 to the 18. So we put like 2 in here, and we have to multiply 2 by itself a gazillion times, right? We compare these two functions. You know, this function starts out real slow. It looks like that other graph here, except it kind of goes up slowly. This function just takes off. This goes along real slowly. Eventually, an exponential function will always catch up with a polynomial function. If we go far enough out that way, and given my scale here, we'd probably have to go beyond the edge of the galaxy, maybe the edge of the universe. Eventually, exponential functions always catch up. They always grow faster. They're close to the fastest growing kind of function we can deal with. So that's something to be, you know, to be aware of. All right. I guess there's one more point about this, how this thing grows. If I take two exponential functions, I'm going to take f of x equals 4 to the x, and I'm going to compare it with f of x equals 8 to the x. Well, they both go through 1, right? 4 to the 0 is 1, 8 to the 0 is 1. But 1, this one's at 4, and I guess 16 is about here. So this is f of x to the, or x. 8, well, 1 is going to be 8. And 2, again, off the top of the chart here. And it's also going to decrease quicker. So the bigger the base, the more quickly it's going to grow. It's useful kind of information to know. Now, before we get to something really useful, we're going to show you something really useful, like how to make money. There's one more kind of abstract mathematical kind of idea we want to go over. Everybody, I think, is familiar with the constant pi. Very important in mathematics. It's 3.14159, and then I don't remember the rest. This number that just kind of goes off infinitely. There's no pattern, irrational number. There's another number in mathematics. This is probably the most important number in mathematics, aside from things like 0 and 1. But there's another number called, we represent it E. E stands for Euler's constant. Euler being a very prominent, important mathematician, who lived around 1300s, did a lot of really good stuff. E, like pi, is an irrational number. It's easier to remember the first digits. They don't keep going like this. They're crazy like pi. That looks like a kind of, yeah, what does that number have to do with it? I mean, pi, at least, we know if you take the circle, take a diameter, you take the circumference, you get pi. If you happen to have a calculator like this, or maybe not one quite as fancy, you might even see on here as an E key. It's important enough if we want to have it at our disposal. We're going to, now I'm going to kind of jump ahead for just a second, don't panic. We're going to look at something called a log. Has anyone worked with logs before? Yeah, okay, you've run into logs. And there are different kinds of log functions. They have a base, log to the base 10. We'll go into what that all means in a future class. There's a very important set of logs. They're so important we give them their own symbol. We say LN for natural logs. We call them natural. And they're just logs to the base E. This number here. So, okay, I'm going to say more about E, but I just wanted to present it. It's an important number. We're going to see it in use in a few minutes. But first, as I said, we have to do something more practical. We have to think about making money. Now, I'm being facetious, of course, but I know some of you are interested in business. If you're interested in business, you're interested in money, you're interested in banks. And if you have money and you put it in the bank and you just leave it there, sometimes you just leave it there so you can pay things. But the bank will pay you money, they will pay you interest, right? So if you put $1 in a bank and, I don't know, this isn't real, but you get 100% interest. Well, at the end of the year, you would have how much money? You get 100% interest a year. Start with $1. What do you have at the end of the year? $2. You have $2. You have your original $1. 100% times $1. 100%, just 100 over 101. You get another $1 and you have 2. Now, after waiting another year, you would have how much? Was that that was your brain thinking out loud, yes. Okay. Let's give this a try. How much? Again, I'm still at 100% interest. I have my $2 now. Okay. Yes.
4.
You'd have $4. That's right. You have your original $4. Your original 2 plus 100% of 2 is 4. All right. Now at this point, my next question should be easy. After another year, how much do we have? 8. Yeah. Yeah, it just keeps doubling. Right? That's what 100% interest does every year. But there actually were bank accounts like this. Not with 100% interest, but which would pay you every year some amount, like, try again. Say you get 5% interest. Well, after a year, you have $1.05. How much would you have the next year? He asks, coming at his calculator. Anybody? Do you have a calculator handy?
1.10? 1.10? Oh. And
Well, yeah, I don't know. It depends what your bank does with that extra stuff. They might just round it off. Yeah. Okay. But most banks don't work this way. Usually they give you a better deal. What they do is they say, we're going to compound, this is called compound interest. You say, instead of compounding it once a year, we're going to compound it, well, it could be twice a year, or 4 times a year. How about every month? Well, how's that going to work? How's that calculation going to work? Okay, so here's the 0th month. That's where we start. First month, they're going to give us 1/12 of 5%. On our dollar. Well, it's not very much. I need a calculator. So 5 divided by 12 divided by 100 times 1 is 0.004. So we're going to have, after the first month, we're going to have 1.004. And then after another month, we got to figure out how to do this better. So I have to multiply that by 1 plus 5. All that work. Now I have 1.008350694. But if you think about it, at the end of the year, I'm going to have more than $1.05, right? Everybody see that? I guess we need a way to express this. We need a way to express how much money we're going to get. The way we do this is we've got an equation. Sometimes we use F for future, or sometimes B for balance. But the future amount is what we call the principal. Principal is the amount you started with, times, well, we're going to have 1 times our principal. We're not going to lose any of it. We're going to get our interest. Well, but as you saw here, we divide our interest by the number of times we compound it. So I'm going to put 12 here for now, and then we'll fix that later. Then, to get a year's worth, we have to keep multiplying it 12 times. And if we want to really make this useful, we could add like a year parameter, right? I mean, this is 1 year, so I put a 2 here, 24 times, that's 2 years. All right, I'm going to update this just a little so you get the real equation. It's n. N for how many times in the year we count it. 12 would be monthly, 2 would be bi-monthly, 365 would be daily. Now, if you go to your bank and you say, I'm going to open a savings account, how much interest are you going to give me? And you say, oh, 3% or 1%. You could ask them, you say, how often do you compound it? Now, it used to be, they might say quarterly or biannually, monthly, but today, they're kind of required by law to tell you they compound it. I want to get the right word here. Continuously. What does that mean? Well, I know that the bigger number I put in here, the more interest I'm getting. But it just doesn't get much larger. It kind of tapers off. And there's what we call in mathematics, there's a limit. This n gets very large as it goes to infinity. And as it goes to infinity, we can rewrite this. We can write this as this is already an exponential equation, because we've got n and y here as exponents. But continuous is P, our principal, times E times our interest times the number of years. Snatched that out of my hat, didn't I? That weird looking number, if you keep increasing n here, you end up with this amount of money. Right? We all want to make money. There's another non-math. It's kind of a math and non-math. It's more of a business thing here, which is most of you here are younger than me. In fact, all of you are. If you start,
How do you know?
I'm not sure. I'm guessing.
You might be right.
I could be right. I might not be. You never want to be too sure. But if you put money away when you're young, like in an interest-bearing account or something that generally makes money, like the stock market. If you start when you're young, like right out of school, when you start making money, and you start putting it away, at first it seems to go kind of slowly, but it's going to increase exponentially. So, by the time you're ready to stop working, you have enough money to live off. Just good advice. All right. I'm not your financial advisor. Okay, let's do some practical numbers here, so we get a little feel for this kind of banking stuff. It's compound interest. We're going to do a real problem. We're going to start with, this would be nice to start with, $15,000 at 8% interest. And we're going to see how much we have at the end of, 6 years. 6 years, okay. And first we're going to do it, we're going to compound quarterly, which means n equals 4. Okay, so let's look at our equation. We've got 15,000 times 1 plus 8%. Well, 8% is 0.08, right? Over 4. 4 times 6, all right? Yes, we learned math. Yes, we learned how to do math on paper, do it on our heads. We're bankers now. We're going to use a calculator. Right? So we've got 15,000 times 1 plus 0.08 divided by 4 raised to the 4 times 6. I can do that. It's 24. I have, at the end of 6 years, 8% is, by the way, a pretty good interest rate if you can get it. You can't get it from a bank today, but you might if you're lucky to get it on the stock market. Okay, that's pretty good. I haven't doubled my money, but, you know, about a 50% increase. All right, let's look at what happens when we do it monthly. So F equals 15,000, 1 plus 0.08, 12, and 12 times 6. Let's take a look at that. 15,000 times 1 plus 0.08 divided by 12 raised to the 12 times 6 is 72. That's 24, 202, 53. Okay, we did a little better. Not quite $100 better. So this didn't really buy us all that much. Well, I have the numbers written down. I don't need my calculator. Okay, let's do it continuously. Continuous means, like, imagine you take it like 360 days and 360, then you break it down to hours, 360 times 24, every hour, then every minute, every second, and beyond. Every insta-second, right? That's the biggest number you can get. So it's 15,000, and the equation is a nice, easy e to the 0.08, that's the interest, times 6 years. The number we get is 24,241.12. Again, just a little bit better. That's as good as we can get. This is what most banks do now. It's not like when you walk in, they look at a clock, you know, and say, you know, how many minutes since you put in your money. But, you know, they'll give you that amount for that day. Yes?
So like, will this, like, financial, like, bank stuff, would that be, like, on the final? Or, like, no? Or just for us to know, like, no?
What we're doing today with exponential functions, and the main thing we're doing with exponential functions is this, right? That could be on the final.
Okay. Oh,
But
okay.
you don't have to memorize the formula because you have 2 sides of a sheet of paper you could write the compound interest formula on.
Oh, we have a
You
piece.
could put this formula for, and if you don't, you might want to just look it up in your book because they'll write it nicer than I have, probably.
Okay, I'll look at it. Thank you.
Okay. Yes?
What word is that under the F for the equation?
It's my mother would say my chicken scratch, just continuous. Continuous. I was just labeling the future value given continuous interest. Principal E, which is this number we talked about, to the interest times the number of years. All right. Okay. All right. This is the heart of today. There'll be some homework, so you do a few problems. I mean, you know, what could be more fun than seeing your money increase, right? You know, you can't think of it. We're going to do something, you know, I've introduced this number. There are lots in math, there are actually a lot of cool things about this number. I could spend the whole class just talking, the whole, from first day to last day. We could do stuff with E. I'm just going to show you one other little magic thing about E. If any of you go on, I think there's at least one person who needs to take calculus in this class at some point. When you get to this, you'll say, I knew that. Mr. Schoenbrun showed me. So if I were to graph this function, this exponential function, e to the x, and I were to take some points on this, points that are close together, very close together. Well, you know, if I have 2 points, there's a line that goes through it. You know, there's a line that goes through it, and that line has a slope. So, for this point here, I could graph the slope. And then for this point here, I could graph the slope. For this point here, I could graph the slope. Same all the way through. So this is kind of a little math magic. If I were to plot all these points, I don't know, does everyone see what I'm doing here? Just taking a little piece of the graph, picking 2 points close together and getting the slope. And I plot the slope for that point. It turns out that you get another exponential function. Now, if I were to graph, like f of x equals 10 to the x, I would get another exponential function here, but it wouldn't be f of x 10 to the x. It would be a different number. E is this magic number where if I graph this function, e to the x, and now I graph its slopes, it's again e to the x. It's kind of magical. Has implications for working with complex numbers, for working with, going to physics. We have something called the differential equation, and to solve differential equations we need this. There's a really, if you haven't run into it, it kind of rivals pi. Pi has a lot of interesting, shows up in a lot of interesting places too, okay. I hope that was entertaining. I hope you got it. This is the important thing. I think there are a few homework problems. I think we're done. 2 minutes. Questions? Now